Okay, so this flipped video is going to cover your favorite topic on the planet, stoichiometry. So I'm going to do 3 quick examples once I go through a few notes that you need to remember. And you need to look at your example problems in the textbook, and there's also the self-check exercises in Chapter 9 that will help you with this if these 3 examples don't help you very much at all. I suggest what you should do as you're looking at the video is maybe watch the first example. With the second example, pause it and try to set it up, and then go back and start it again, and then see if you're following the same process that I'm following. So for your viewing pleasure, I'll take my picture off the page and we'll get started. Just for a basic definition for review, remember that stoichiometry is the process of using a balanced chemical equation to determine the relative masses of reactants and products involved in a reaction. And the key here in this is going to be it's a balanced chemical equation. So make sure it's balanced before you go any further. There are steps for calculating the masses of reactants and products in a chemical reaction. The balance equation is essential, so you have to start with balancing the equation first. Convert masses of reactants or products to moles. Use the balanced equation to set up appropriate moles-to-mole ratios. Use the moles-to-mole ratios to calculate the number of moles of the desired reactant or product. And the last thing is to convert from moles back to masses. One of the things you need to remember, and we've used this before, is you can go grams to moles. Remember that you do a mole-to-mole ratio at that point and then can turn moles back to grams. You can start at any place within this. If given grams, you can go to moles, do a mole-to-mole ratio, and leave your answers in moles if that's what's required. If not, you're going to change it on into grams. So let's look at a couple of examples. Here's the first one. How many grams of chromium 3 oxide can be produced from 15 grams of solid chromium and excess oxygen gas? And here is your equation. The first thing that you're going to have to do is look at it and see if it's balanced. So I have one chromium here, 2 chromiums here. So I'm going to have to put a 2 out in front. So now I have 2 chromiums, 2 oxygen, 2 chromiums, 3 oxygen. So we're going to have to balance the equation like this, which is going to cause this number to change. So we have 6 oxygen here, 6 oxygen here, and now 4 chromium. So we change our coefficient to 4. So now we have a balanced reaction. The next thing you do is write down all the information that you have underneath where it goes with the reactants or the products. So it wants to know how many grams of chromium 3 oxide can be produced. So X grams from 15 grams of solid chromium and excess oxygen gas. So remember, in this case, excess means I have more than I'm going to have to ever worry about needing enough of. So that's what we're going to start with. So this excess means we really don't take it into consideration. So let's write our scheme up here again, just to remember. So grams to moles, mole-to-mole ratio, and moles to grams if needed. And we're starting at grams, which is here. And we want to get to grams, which is here. So we're going to have to go through the whole process. Remember that you can't compare mass to mass because masses aren't important. It's the number that we have to deal with. So we have to change grams to moles of chromium. So we're going to start with chromium. And after consulting my periodic table, I know the mass of chromium. So we're going to start, I'll just jot this down here from the periodic table. So we'll have it as 51.99 grams per mole. So we're going to start by taking 15 grams of chromium and changing it to moles. So 1 mole over 51.99 grams. And it's set up correctly because I can cancel my grams. So I'm going to take 15 divided by 51.99, and I get 0.289 moles of chromium. So I've gone from grams to moles. Now I need to look at my mole-to-mole ratio. So I'm going to look at chromium and compare it to the chromium 3 oxide. And the top number I'm going to get from my balanced reaction. So chromium from the balanced reaction is 4 to 2, which is the ratio they react in. And for my problem, which is the bottom number, it'll be my problem, I have 0.289 moles of chromium, and I need to find out how many moles of chromium 3 oxide that can produce. So I'm going to cross multiply. 4 times x equals 2 times 0.289. Divide both sides by 4. So I get x equals, and that's 2 times 0.289 divided by 4 equals 0.1445 moles of Cr2O3. So I've gone from grams to moles. I've done my mole to mole ratio. Now I change from moles to grams. So the first thing I need to do is find out what the molar mass of chromium 3 oxide is. So I have 2 chromium weighing in at 51.99 grams per chromium mole of chromium. I have 3 oxygen, which is 16. So 2 times 51.99 is 103.98. 3 times 16 is 48. We add those two together, and I get 151.98 grams per mole. I need this information in order to change moles of chromium 3 oxide back to grams. I'm running out of room. I'm going to bring this over here. I'm going to say I have 0.1445 moles of Cr2O3. I'm going to change that to grams by using the molar mass. So I'm going to take 151 grams, 151.98 grams over 1 mole, cancel my moles, multiply 0.1445 times 151.98, and my answer is 21.96 grams of Cr2O3. And that's my final answer. Now, I know this problem was long and drawn out. It's kind of messy the way I've set it up. It's not an easy flow to it because I kind of ran out of room. But this is the basic maximum messy problem that you can come up with when we do stoichiometry until we get to limiting reactants, which is tomorrow. But when we look at this, this is what we're looking at. This is how you do these problems. You write down the information that you know, make sure that your balanced equation is there, make sure you've done that correctly, and you start with what you know and go to where you want to get by using this scheme right here. Let's look at exercise 1. If you feel comfortable with the example that was given right before this one, you might want to pause this at the very beginning and try to work the problem out yourself and then check and see how I went through it. If not, watch this example and then we'll go on and have another example as well. Tin 2 fluoride is added to some dental products to help prevent cavities. How many grams of tin 2 fluoride can be made from 55 grams of hydrogen fluoride if there is plenty of tin available to react? So this is the equation that I'm dealing with. Tin 2 fluoride is made according to the following equation, and if you notice, it's already balanced, so that's one step that we don't have to do. So the next thing that we have to do now that we realize that it's balanced is we have to take it and write down the information underneath everything, each individual compound. So it's added to some dental products to prevent cavities. That's not necessary for our problem. How many grams of tin 2 fluoride, so here's tin 2 fluoride, and I want to know grams, can be made from 55 grams of hydrogen fluoride, which you know is actually hydrofluoric acid, so 55 grams. If there is plenty of tin, so excess tin, we don't have to worry about how much tin that we're dealing with here because we're going to have plenty. So I know grams to moles, mole to mole ratio, and moles back to grams is where I need to start. So we are at grams and we want to get back to grams. So this is really similar to the last problem that we did, where we're going to first of all start by changing grams of hydrofluoric acid to moles. So we have 55 grams of HF, and we're going to change it to moles. And I'm going to pause and get some information on the screen and come back, and it'll already be there to save us time because the screencast is timed. So just bear with me. You'll see new information pop up. That way we don't have to take time to go through and calculate all of it. So the first thing we have to do is to find out what the molar mass of hydrofluoric acid is. So I've had 1 hydrogen, 1 fluorine, and I go through and do the calculations, and I have 20 grams per mole. So I put 1 mole on top, and I put 20.01 grams on the bottom so that my grams cancel. So I take 55 and I divide it by 20.01, and that leaves me with 2.75 moles of hydrofluoric acid. Now, I've gone grams to moles. I need this mole to mole ratio between what I have and where I want to go. So I have hydrofluoric acid to 10,2 fluoride. Remember, the top one is from the balanced reaction, and the coefficient is 2 here. The coefficient in front of the 10,2 fluoride is 1. The bottom number is from the problem, and I have 2.75 moles of hydrofluoric acid, and I need to know how much 10,2 fluoride that's going to make. So I take and cross multiply and solve for x. So 2.75 divided by 2 is going to be 1.375 moles of SNF2. And just as a check, if you we'll go back and look and take time to set it up this way, the x is under the 10,2 fluoride, and that's what I solved for, was the 10,2 fluoride. Now I've gone from a mole to mole ratio, and my answer asks for grams. So I'm going to take the 10,2 fluoride and I'm going to change that to grams. Our next step is to go through and find the molar mass of the 10,2 fluoride, which I've done here, taking 1 times the mass of 10, 2 times the mass of fluorine to get 156.71 grams per mole. So I'm going to take the number of moles and change it back to grams as per the problem requested. So I'm going to put 156.71 grams on the top, 1 mole on the bottom so that they cancel. So I'm going to take 156.71 times 1.375, and my answer is 215.48 grams of SNF, and SNF2, and I'm going to take this opportunity so that it makes limiting reactants a little bit easier to bring to your attention that this is the theoretical yield, because obviously when we go into the lab we never recover 100% of anything. So theoretically this is how much 10,2 fluoride we should be able to come up with. So the next one is exercise 2. Again, if you want to get it started and pause it so you can go through and do the work yourself and then check it, that would be a great idea. Alright, I've already got this set up due to time on the screencast-o-matic. So it says we have 20 grams of PCl3, and we want to know how many grams of H2O that we need to react completely with it. So the products have nothing to do with this question. We already have a balanced equation. I know my mass of PCl3 is 137.32. I put that in that's my grams. I go to my mole to mole ratio. That's my grams, and I change it to moles. So it's 0.146 moles of PCl3. I now do my mole to mole ratio, and I should end up needing 0.438 moles of water. And I know that the mass of water is 18 grams per mole, so I multiply that times 18, and my final answer is 7.884 grams of water needed to completely react with 20.9 grams of PCl3. And this is important that you realize that sometimes they're going to be asking for how much reactant I need to react with another reactant, as opposed to how much of a product that I'm going to be creating. So there's 2 great examples, 3 if you count the first one. Go to your textbook, use your examples in your textbook if you're still not sure, and you'll get time in class tomorrow to work on the assignment.